Okay, so we're going to talk about solubility today. Specifically, this is the topic of KSP, or solubility product constant, from the AP curriculum. This is a quick intro / review in preparation for the AP exam. From our textbook and class, this is chapter 17, sections, I believe, 4 through 6. So we've seen solubility before, obviously, when we talk about precipitation reactions. And back when we talk about it in that context, we basically have two categories. We had soluble and insoluble. And we just kind of assumed or pretended that insoluble meant does not dissolve in water. But it turns out that that's not technically true. That even substances that are considered insoluble do dissolve to a very small extent. You put something in water that is ionic but categorized as insoluble, there is a very small amount or few ions produced. So we can conclude that there is a small amount that does dissolve. Now, it will not completely dissolve. The substance will dissolve, will move towards dissolving until equilibrium is established. In the case of insoluble compounds, or compounds that are dissolving, they dissolve to form a saturated solution. So if you remember back when we first introduced things dissolving, we had this concept that this process of dissolution occurs, and in some cases the ions that are produced reform the original, a process called crystallization. Now, we don't typically see it in that way. We typically have the word dissolution written above the arrow here, but basically what I'm implying here is the forward direction, dissolution, and the reverse direction, crystallization, can be equal in speed, and therefore we establish equilibrium. That is a saturated solution, a dynamic process. So we're going to apply that concept and the math we've learned with equilibrium problems, specifically the ice technique. We're going to apply that to concepts involving insoluble ionic compounds. For example, silver chloride. It's considered insoluble. Well, it turns out that silver chloride in water will slowly dissolve until an equilibrium is established, given by or represented by the law of mass action, like any other equilibrium. In terms of molarities, it is the products raised to their exponents divided by the reactants raised to their exponents. So therefore, for silver chloride, we have silver ions to the first power times chloride ions to the first, divided by the reactants. Well, the reactants are a pure solid, so there is no reactant here. And that equilibrium value, expression, has a constant value known as obviously K, as any equilibrium would be. We give it the subscript SP, which stands for solubility-product constant. So anytime you see that SP subscript, it's referring to a solubility-product constant, an insoluble ionic compound. And those values are published, often given in a problem. In this case, 1.8 times 10 to the negative 10th. So this relationship here is the quantitative version of the equilibrium expression for silver chloride. Now remember, when we're talking about K values, the magnitude of K tells us the tendency to occur. The higher the K value, the more soluble or the more favorable the forward direction is in this case. And therefore, the lower the K value, the less favorable the forward direction is. You could say the higher the K value, the less favorable the reverse direction is, and the lower the K value, the more favorable the reverse direction is, if you desire to do so. Now, there are three approaches we're going to follow. I'm going to give examples of each as quickly as I can. First is finding KSP from solubility. The second is finding solubility from KSP. And the third, will it precipitate form? So to address those three, I'm going to do a couple quick examples. The first example we're going to do, let me get to some problems from your text. Hopefully that will help demonstrate this. So this first one is here. This is an example of finding KSP from the solubility of a compound. So a word about working with solubility. Okay, so
Ms. Fonseca to the bookkeeper's office, please. Ms. Fonseca to the bookkeeper's office.
For a compound, for example, we'll go kind of not address this question yet. For a compound such as silver chloride that I was mentioning a few moments ago, its solubility is defined in terms of the original compound. So I'm going to put solubility under it and tell you that solubility for silver chloride equals the moles per liter that dissolve in solution. Now, sometimes solubility is reported in grams per liter or grams per whatever. Just remember, if you do find it in moles per liter, which we will, KSPs work with molarity, so when you find it in moles per liter, if you're asked to report it in grams per liter, you would just convert the moles to grams using molar mass, for example. Okay, so the solubility is defined in terms of the original, and the original compound is related to the ions through the stoichiometry. So in all these questions, we're going to basically do the following. We're going to make this statement that let X equal solubility. That statement alone is going to help us a lot. We're going to use that X value just like we did with the acids and bases in their equilibrium expressions, and the ice technique is going to be exactly the same. So we're going to take that approach here. Now, in this question we're asked, it says solid silver chromate is added to pure water. Some of it remains undissolved at the bottom of the flask. That phrase is a clue that the solution is saturated. So it has reached a point of equilibrium. It says it's waited. We take several days. We make sure equilibrium is established. And in that solution at equilibrium, the concentration of silver is 1.3 times 10 to the negative fourth power. Assuming that silver chromate dissociates completely in water and that there are no other important equilibria involving them, calculate KSP. Now, that phrase, it dissociates completely, they're not implying that it's 100% ionized. They're implying that it has established equilibrium and there is no other side reactions going on. So the only substances present are the ions from the silver chromate. Maybe it would help if I wrote the reaction for silver chromate. Okay. Now, back to the previous kind of introductory example before we get to the problem here. For any substance, if we define the solubility as X, we can determine the amounts of the products in terms of X, just similar to what we did with our ice technique. So reminding ourselves of the ice technique for equilibrium, suppose we put this pure silver chloride, which this question is not directed towards, but we put that solid silver chloride in water and it established equilibrium. We could use the following statements. Assuming we define solubility as X, the moles per liter of silver chloride that dissolve. So we would say the original amounts of these are 0. The reaction would shift to the right, establishing our trend or change as positive, and the magnitude of that change related to the coefficients here. Add down, and we get to a point where we had an equilibrium expression we could sub into, or X squared. Now understand, this original definition allowed us to make these statements because the number of moles of silver that comes from the silver chloride solubility is 1 to 1. It's a 1 to 1 ratio. So it's the same X, making that substitution in the law of mass action like before. Now we're going to apply this idea down here, but there's one difference. At the end of those problems with acids and bases, typically we would substitute the X's in and we would have a K value, like a Ka value for example, and then we'd solve for X. But in this example up above with the silver chloride, we don't have the KSP value. We're finding the KSP value, so we need another clue, and that's where this number here, this 1.3 times 10 to the negative fourth, comes in for the silver chromate example. We're going to use that number along with that ice technique in the following way. We're still going to let X equal the solubility of silver chromate. And so that allows us, you can use the same ice technique, and the initial amounts are still 0, but please note that the amount of change from silver's perspective is 2X, chromate 1X, adding down we get this and we get that. Now that number, that 1.3 times 10 to the negative fourth power, that number represented the concentration of silver ions at equilibrium, which we know is 2X. So, combining everything I've said, that solubility is defined as X, that the concentration at equilibrium for silver in this example was 1.3 times 10 to the negative fourth, and that using the ice technique we know that the concentration is twice the solubility because of the mole ratio, we can solve for X, which is the solubility, as 6.5 times 10 to the negative fifth moles per liter. In addition, we can substitute into the law of mass action, the KSP expression, Let me move these out of the way for us. That'll be in the future. So we can substitute into that KSP expression for silver chloride, or excuse me, silver chromate. The KSP expression for that one would be the silver ions to the second power, chromate to the first power. Substituting in, we see that it's silver ions is 2x to the second, chromate is x to the first. Doing a little math, that's 4x squared here times x, 4x cubed, and that, remember, is equal to KSP. Now we solved our x value earlier, so I'm going to substitute my x value in place. 4 times 6.5 times 10 to the negative 5th power cubed equals KSP. So doing some arithmetic using my calculator, I get an answer of approximately 1.1 times 10 to the negative 12. It's a unitless quantity representing the equilibrium constant for silver chromate in solution. Now, please notice we took solubility, or an amount present at equilibrium, and we went backwards to determine the KSP. Now in the second example here, we're going to do the other process where we're going to determine solubility. Here's an example here. So let's read the question. The KSP for calcium fluoride is 3.9 times 10 to the negative 11th. Assuming that it dissociates completely upon dissolving, meaning there are no side reactions, calculate the solubility. So remember what I told you. We define solubility as X. So writing the expression in this form, writing the KSP expression off to the side, now we should have enough information. KSP is given, we'll get back to that in a second. So because this is a solubility product constant, I'm going to say X equals the solubility. And if X equals the solubility, then that tells us that the change in terms of to establish equilibrium is X, and the change here is 2X. Adding down, substituting in, and including the solubility product constant from the prompt. Now we're going to solve for X. Remember, X represents the solubility. So a little bit of math. 3.9 times 10 to the negative 11th equals, again, 4x cubed. So give me a second here to solve that on my calculator. And we get an answer of approximately 2.1 times 10 to the negative 4th moles per liter, which represents the solubility. So there's a second type of example. Now in the last example here, it says, will a precipitate form when 0.1 liters of 8.0 times 10 to the negative 3rd molar lead to nitrate is added to 0.40 liters of 5.0 times 10 to the negative 3rd molar sodium sulfate? Well, the key thing to understand here is, first of all, we have to recognize what compound might be formed, the precipitate, if you will. So in this case, I think it's fairly obvious, skip a few steps, that we're going to have lead 2 and sulfate. So this is the likely precipitate. Now, we can look at a chart and we can see that it is labeled as insoluble, but that doesn't mean that a precipitate will actually form. Remember, this substance, being listed as insoluble, will establish an equilibrium to form a saturated solution, but that will only occur if equilibrium can be reached. And remember, at equilibrium, the concentration of the lead 2 ions times the concentration of these sulfate ions will be equal to the K value. Now, if it turns out that in our solution, the product of lead and sulfate is not equal to K. Remember, there's 3 possible combinations. The first one is that the combination that is present, which by the way we call Q, the reaction quotient, if we determine that the conditions listed in the problem, the current conditions, and we substitute those values into this expression, if we find that those current conditions, called Q, the product is equal to K, or KSP, then we can conclude that it's at equilibrium. Or in other words, it is saturated and therefore a product or precipitate is formed. In the rare cases where Q is larger than K, that means it's beyond saturated. You could even call it supersaturated, I suppose. And what you would slowly get is the reverse reaction would dominate, and you would actually form more precipitate in that case. Or the last option is that Q is less than K, meaning that there are not enough ions and it is not at equilibrium, or no precipitate. Now this is important to understand. If you're mixing the ions and the product does not reach the magnitude of K, that means that there is no precipitate forming. If there was more solid undissolved, then the undissolved solid would continue to dissolve, increasing these values until equilibrium was established or the solid completely dissolved. So that's an important point to make. In this example, there is no precipitate initially. Therefore, it simply comes down to finding the current state, Q, and deciding which of these three applies. If there was solid lead sulfate present, lead 2 sulfate present, but we had not, but the concentration of ions was not sufficient or not high enough to equal K, then the lead 2 sulfate solid would dissolve until it was equal to K, or there was no more lead 2 sulfate to reach that point. So let's apply that reasoning. We're gonna find the moles of each ion, the molarity of each ion. We're going to substitute into this expression and compare the K value to the Q and see what happens. So you can see here in this first part we have 0.1 liter of this molarity lead 2 ions, and we also have 0.4 liter of 5.0 times 10 to the negative third sulfate ions. Let me do a quick calculation here. I can do that one in my head, believe it or not. That's that many moles, and we get don't trust my own arithmetic. This many moles of sulfate ions, but remember we need molarity, so I divide that by the total volume, which is 0.5, which means I get 16 times 10 to the negative fourth, or 1.6 times 10 to the negative third molarity for this, and in this case I get 4 times 10 to the negative third molar here. So if I substitute those values respectively here and here, I get 6.4 times 10 to the negative sixth. Well, if we compare that value to the published K value, which is not here, would have to be given on a test, one of three things would occur, as I said. So if we find that this value, Q, is greater than K, it is over that point, so yes, a precipitate would form, and if it was less, no precipitate would form. So that's kind of the rundown. Check examples, AP examples posted online. Specifically, 2010 has a very good problem. I think it's 2010 version A, question number 1. Good luck.